Okay, so thanks a lot, everyone. So it's a pleasure to present this paper immediately after the keynote. So in some way, it is a vision that is well connected to what Betty was saying about these smart systems. So as you can see, it's a vision paper with a lot of colleagues. So it's a big pleasure to present this paper, and also it's a big challenge to to present this paper. That's is an outcome from the winter modeling meeting that we organized in 2023 in the north of Italy, in a very fantastic place with a lot of researchers interested in model-based engineering, model-driven engineering, and language engineering. So briefly, the MOL team. So we meet in this fantastic place to understand the status of model-driven engineering in general, and how we could revamp a model-driven engineering foundation in order to be more promising for students, researchers, and also practitioners. So during this meeting, we had a lot of discussions. But first of all, let me say, we discussed a little bit about which kind of system we want to consider in order to contextualize the discussion and to see what future we can have in this domain. And from system, we talk about ecosystems, so in systems that include the aspect of socio-technical. So we have a human in the loop, we have the social aspect that is very important, especially because we have the humans, and we have the growing of data information and also AI that is in the system, but we need to consider also the human. The second aspect is the heterogeneous aspect of the technology that we have in these kind of ecosystems. So a lot of technologies that can manipulate the different data in different ways. Okay? And of course, that involve the diversity of stakeholders. So humans is okay, but we have different type of technology, different type of devices, and different type of interest in this kind of ecosystem. Starting from the citizen, including also public administrations, we can involve schools, transportation means providers, and so on and so forth. Of course, these kind of systems are complex in their nature, so they are dynamic, and we can include in the same system different application domains that can, in some way, integrate and share different aspects and interests, and even challenges. Of course, AI is here, as we already listened from the keynote. AI is a big component that we have in this kind of system, and we need to integrate these AI components in these ecosystems. And we have the integration aspect, we have more intelligence in these systems, and of course, adaptation is one of the core aspects that we need to manage and consider while we are designing the system, but also we are operating at runtime with this kind of systems. So we discussed about how we can engineer this system that are complex and not complex every day. Of course, we know the V model, so we start from the conceptualization of the system. Of course, we need to define the requirements and all the details from the architectural perspective. We need to detail the design until the implementation. We integrate all the components, and we want to test the system and verify all the aspects during the testing and integration through verification and validation techniques, and we reach the operation and maintenance time. But of course, during this process, we have a feedback loop that is continuously running, where we measure data, we assess some phenomena, so we monitor some aspect, we adjust respect to this analysis, and we act through the implementation of the adjustment directly in the system. Of course, in this period of the time, with a lot of data that are running and that are available, and especially when we have the AI components that we need to manage, this loop is more challenging, no? And we need to revise also this model and in general the engineering task. So this means that this often As we said, a lot of challenges and a lot of aspects we need to take into account. First of all, we have multiple experts in the same system. So what we discover is that we have system engineers, we have software developers, we have data scientists, and we have simulation experts. All these experts are part of the same system. Often they operate in silos. So of course, this will bring in the limitation of a lot of opportunities and collaboration, and especially in the knowledge exchange. So we need to solve this open point. The second aspect is that we have a fragmented reality. So we have different modeling communities that share the same mission, but they are yet in working in isolation. So we need to find a way to put together all these communities together in order to realize these type of ecosystems. So starting from this analysis, we start to also to think about the concrete example. And the concrete example was about the city twin. So in some way, we want to have a twin of a city where we want to understand phenomena, and we want to analyze data in order to retrieve and understand what we could do at runtime on this kind of system. We derive a specific example. So that you can see this slide. Of course, it's one toy example but that open up a big discussion among the participants to this event. And what this example about real-time emergency alerts and recommendation to citizens in order to react to the specific situation, in order to avoid, for example, congested roads, for example, to deploying snow plows, a strategical planning task in order to understand what are these critical routes. We want to notify the citizen about alternative and how they can use the transportation options in order to react to this situation. In some way, we want to enhance the city resilience to make the city more safe, more adaptive, and sustainable for the future. So this kind of example put on the table this aspect of multi-view and multi-model specification, because we involve a lot of stakeholders. They bring on the table different models, but we need to manage this complexity on this kind of urban mobility scenario in order to, let me say, manage the challenges of this kind of model cities in this specific scenario. So of course, it is a dynamic ecosystem because the city evolves, the city can adapt in order to maintain the efficiency and the effectiveness of the entire urban infrastructures. So models are there. Each model represents a specific phase of the city. This model should be synchronized in a certain point in order to adjust and ensure that the management of the mobility of the city remains dynamic and responsive in order to manage these changing conditions. So the uncertainty is there, and the models can also change respect to the context condition, like weather condition or unexpected events, and also diverse daily movements of thousands of citizens that are living the city. So in order to manage this, of course, as I said, we have different models that can start from the city infrastructure models, like road networks, public transportation system, or emergency response facility. We can have, for example, data from the past, so historical weather data that we can use in order to understand some condition for the forecasting that can be repeated in the time. So we can have models that represent, for example, the weather, real-time weather data in order to assess the effect of the snowfall, of road friction and traffic flow. We have the traffic flow model, real-time data from sensors and from companies that manage the traffic transportation. And of course, we can have also model transformation. So how we can transform models in actionable plans in order to check the consistency and the coherence between different models. So this scenario open in some way the characterization of the three pillars of our vision. So for example, we can exploit the experience from model-based system engineering in order to analyze the different data in order to understand what is the capacity of the different roads in a specific moment, the location of the bus stop, the availability of some emergency response resources. we can pass through the modeling and simulation, or we can simulate from data, so we can understand what will be the impact of heavy snow or road conditions, the potential for traffic congestion, the effect of snow accumulation for public transportation schedules, and so on and so forth. The data science and AI can help us with insight, so we can understand, for example, the weather condition in the next days, for what is the amount of the road blockages in the next future, or what will be the public transport delays upon to this context-aware condition that is changed. Model-driven engineering, of course, will help us to automatize processes, so we can transform models in actionable plans in order to ensure the consistency and the coherence between the models, so we can manage the consistency management, we can align models and real-time data using these subcomponents of this our ecosystem. So, of course, all the discussion open to a set of research challenges. Here we can see a set of key challenges. For example, the first one, we need to characterize in a systematic way and connect all these heterogeneous data that are even complex. So we can create an efficient model as a service in a collaborative environment for system engineering, in order that these engineers can, in some way, manage the models in a collaborative way and can use each model as a service in order to characterize the ecosystem. We would like to improve the fidelity of the data and the accuracy of the data, and especially of the models that are built on top of this data. We need to maintain the separation of concerns because they are different disciplines, but of course, with their characterization, and we want them to collaborate. So we need to support the sustainability of this kind of system, and especially of their life cycles, because we have more life cycles inside the system. We need to incorporate reliability in the system engineering with consideration of explainability. So we need to explain phenomena, we need to explain phenomena to the citizen, speaking a specific and the right language. We need to maintain the trustness and the ethics when we use especially AI components. We have also an overarching challenge that, of course, is traversal to all the other challenges. We need to improve the training and education for this kind of integrative engineers. So after the challenges, of course, we analyze what are the neighbors that we already have that can guarantee this integration and this, let me say, management of this ecosystem. The first key enabler is the abstraction. Of course, we need to represent different aspects of the system at a different scale and a different time scale. So we need to have abstraction in the loop, but we need to have abstraction with the appropriate fidelity. That could be high fidelity or low fidelity, depends on what we want to use the abstraction. We need to manage also the semantics of these models that are heterogeneous. We have different representation, but we need also to use the abstraction also to continuously refine the system modeling, simplifying some aspect in a certain condition. We need to trace these refinement, and we need to also identify simplification gaps and also prevent errors to manage the inconsistent introduction in this kind of abstraction. The second enabler is integration. Of course, we need to integrate the different aspects, starting from their processes. So we need to include the different modeling paradigms that could be discrete modeling or continuous modeling. We need to manage different views of the system, maintaining also the right level of abstraction. So while we are implementing the system with these models integrated, then we need also to manage the evolution of systems. For example, analyzing data and using also the models, we need to support the system in order to manage the variance, to manage the versions of these systems. And the system is complex, and of course, this is very challenging. So modeling multiple systems with multiple variants and with multiple versions, we introduce a lot of difficulty that we need to manage. Okay? And we need also to analyze, so to introduce tools in order to analyze the evolution space and give a lifetime support in order to understand the different phenomena. Data and models are there. So we have a lot of data, we have a lot of knowledge of the system. We need to validate the data. We need to adapt models on the fly when we have this adaptation of data. Since the system is evolving continuously, we need to understand also what is the impact of the analysis of this data. When we discover, for example, uncertainty, we need to quantify also the quality of the data and also the impact of these updates. So model mining techniques could also be used in order to increase the data size, but also the quantity and the quality of the data. Quality is another key enabler. So we need to assess the quality not only of the data, but also of the adaptation of the system, of the models that we are using. So the impact of the data that could impact the model quality. And we need also to trace all this information and repeat in a long way also the analysis that we can do. The last key enabler is the user experience. Of course, we need to explain the analysis result to end user, to the citizen, to the different stakeholders involved in the system in order to give an effective and efficient modeling experience. So the models are there, but we need to explain what the model represents, not only to explain some results, but also to engage the citizen, engage the stakeholders in some participatory design activities and collaboration. So all the key enablers will be connected to the four pillars, and of course in what we call an integrative modeling. So in this picture, you can see how, for example, model-based system engineering will, let me say, converge or contribute to the specific enabler as the other components. So what the end we derive from this discussion, and that is the outcome. Our vision is that we need to have an integrative paradigm. So the picture on the left of these slides has as a center element the modeling component. So we need the model at the center, but we have a model as in some way a connection between all the four disciplines. And in order to do this, we need to have an integrative paradigm shift. So we need to shift versus an holistic modeling approach in order to bridge model-based system engineering, model-driven engineering, modeling and simulation, and data science and AI in a unique paradigm. So the city twin is an example that demonstrates the need in order to have these integrated modeling in order to capture, simulate, and optimize complex systems across public and private stakeholders. Of course, we need to maintain the synergistic aspect of the model. So starting from requirements and architectural definition, code generation, adaptive intelligence, and validation of the system behavior to simulation, all these aspects should be maintained and be consistent with the models that we use in this kind of complex system. Of course, we cannot do this without to guide the research direction and to guide the education. So this means that we need to create a new profiles, a new researchers. Of course, we need to implement the new innovative modeling tools that are able to maintain this complexity and also this synergy between the models from different perspectives. So we need to have a multidisciplinary education in this picture in order to prepare future engineers for cross-domain collaboration. So to close my talk, so modeling in our vision is the key to mastering this complexity. So we need this paradigm shift to integrate modeling as we have derived from this paper. And we need to, let me say, guide the future engineers in order to understand what is the integration of models, in order to have a unique picture between the system engineering, software engineering, data science, and simulation through three principal aspects: collaboration, innovation, and education. So you can find the paper on this picture. You can scan and you can download the preprint of the paper if you are interested. And I'm here for your questions. Thanks a lot for your attention.